Hello, welcome back. Let's look at theorem 5.5. What this says is a vector x is in the orthogonal complement of the span of a list of vectors if and only if x is orthogonal to each vector a1 through ac. In other words, x dot a1 equals 0, x dot a2 is 0, up through x dot ac is 0. Now, if you look at the pictures that we have before, I think this should be pretty intuitive. Like the vector x in the span of a1 through ac's orthogonal complement is like a vector in these red subspaces before, like some linear combination of the v and w in this picture. So somewhere on the red plane. And as long as you're orthogonal to b, you're going to be orthogonal to any scalar multiple of b, is basically what this is saying. Let's look at an example. This says let A be the matrix with columns A1 and A2, which are our three columns. Let's describe the column space of A's orthogonal complement. Now, remember, the column space of A is the same thing as the span of A1 and A2 by definition. So theorem 5.5 applies, and we can say that x is in the orthogonal complement of the column space of A if and only if x dot a1 is 0 and x dot a2 is 0. And just like before, let's write x as x1, x2, x3. So a1 is the column 1, 0, 0. So x dot a1 means x1 times 1 plus x2 times 1 plus x3 times 0. We want that to equal 0. And likewise, x dot a2 also needs to be 0. And saying that the vector x satisfies both of these is equivalent to saying that the vector x is a solution of this matrix equation, because like getting this 0 here, just using the row column rule, you would do 1, 1, and 0 dot producted with x1, x2, and x3. And likewise, to get the second 0 on the right side of this, you do the row 1, 0, 1 dot producted with x. So we just need to solve this system of equations. We can basically just row reduce it. Like I could replace row 2 with row 2 minus row 1 to get a 0 here. 0 minus 1 is negative 1. 1 minus 0 is 1. Then we can clear away this one and also scale row 2 by negative 1. And this is what we'll get. So now this is saying that, because this is in reduced echelon form, we have x1 plus x3 equals 0 and x2 minus x3 equals 0. We can write x1 as negative x3. We can write x2 as equal to positive x3. And x3, the free variable, is always equal to itself. So this is saying x can be written as x3 times negative 1, 1, 1. And remember, x is in the orthogonal complement of the column space of A if and only if x is a solution of this matrix equation, if and only if x is a scalar multiple of -1, 1. So we can say the column space of A's orthogonal complement is the span of -1, 1. And let's also notice that what do we have right here? This is the same thing as taking the columns of A and turning them into rows. So this is the same thing as saying A transpose times X equals 0, which is equivalent to saying X is in the null space of A transpose. So we could also write this column space of A's orthogonal complement as the null space of A transpose. In the picture here, we can see here are the columns. A1 is on the x1, x2 plane, and A2 is on the x1, x3 plane here. So the span of them gives you this sort of diagonal plane here, the column space of A. And the set of vectors that are perpendicular to each of those A1 and A2 vectors gives you this whole column space of A perpendicular. And again, we saw why being perpendicular to each of these means that you could write that as A transpose times X gives you the 0 vector. So we're also talking about the null space of A transpose. Okay, now theorem 5.6, we've kind of been describing why the first part of this is true with a bunch of examples. The first part says the column space of A's orthogonal complement is the null space of A transpose. And the gist of the proof of it is like in this example, that the null space of A transpose means when you do X times A transpose, you're essentially doing a dot product of X with a column of A and getting 0. And same thing with all the other columns of A. So I'm going to say, let's skip the proof of 1 because we've already seen enough examples. The textbook has a formal proof, and examples 5, 6, and 7 I think should justify it pretty well. But let's prove the second part, because we haven't really been talking about the row space of A or its orthogonal complements yet. And the proof of it is actually kind of cute, kind of fun. So the row space of A's orthogonal complement. Well, what is the row space of A? What does that mean? We mean the span, the set of all linear combinations of the rows of A, but the rows of A are columns of A transpose. So the vectors in the column space of A transpose are the same vectors as in the row space of A. They're the same thing. Now, what we can do with this is apply part 1 to this, because we still have an orthogonal complement of a column space of something. It's just the column space of A transpose instead of A. And what does part 1 say? It says that the orthogonal complement of this column space is equal to the null space of that A transpose, but transposed, right? We still have that transpose here. But the transpose of the transpose is just A itself. So this is the same thing as just the null space of A, since A transpose is just A. And we went from here to here using part 1 of the theorem. So yeah, that's it. That's the proof of part 2. All right. Now, this can be a tricky one to remember because you have all of these transposes these t's, and also these upside down t's floating around. I think a good way to remember it is just to sort of think about this all important step here, that doing A transpose times X and getting 0 is the same thing as doing a dot product with the columns of A and getting 0, which means you're orthogonal to the column space of A. All right, let's look at theorem 5.7. This says if W is a subspace of Rn, then W perpendicular is also a subspace of Rn. We saw that with all of these examples. Like, we were able to write the orthogonal complement of all kinds of things as a span of some vectors, which is also a subspace. Part 2 is maybe more interesting. This says that the dimensions of the original subspace and its orthogonal complement add up to n if we're talking about vectors in Rn. This is related to the rank nullity theorem. By the way, I forgot to mention that in Gilbert Strong's linear algebra textbook, he calls this the fundamental theorem of linear algebra. Some other people call the rank nullity theorem the fundamental theorem of algebra, but nobody really agrees on what theorem of linear algebra is the most fundamental. So anyways, let's look at part 3. This says the orthogonal complement of the orthogonal complement of W is equal to W itself. And maybe that makes sense. Like, if you take this red line here and think about what is the set of all vectors that are perpendicular to it, you're going to get points on the blue plane, right? Seems intuitive, but it actually turns out to prove this is the trickiest one at all. When I was teaching linear algebra for years, I just looked at this and said, oh, of course this is true. And then I didn't realize until last year that there's actually some work you have to do to prove this. So you can read the proof in the textbook if you want, but it is true. Let's save the last example for the next video. So I will see you then.